All right, good afternoon, everybody. So this week starts a new topic in the course. So we're going to move on from AI, and we're going to talk about physics in a game, in a game engine. All right, so we're talking about game physics now. This is one of the problems with teaching these graphics-based courses to computing science students. And so to talk about computer graphics, computer animation, video games, you eventually have to start talking about physics. And as computing science students, you don't have to take an undergraduate physics course. It's slightly worse in this course because what you really want to talk about isn't normally taught in undergraduate physics until second or third year. So in reality, you actually need several undergraduate courses to actually understand what's going on inside of a modern game engine. And so we're not going to get the full, I'm not going to tell you everything about the physics that's happening inside your game engine. I'm going to try to get far enough that you can do something interesting in 2 and 3D. All right, so what is game physics? Basically, the physics in your game controls how things move and how objects react to one another when they collide. Right? And so we've seen a little bit of physics so far, right? So when we talked about path planning and moving things around, we talked a little bit about game physics, right? So to compute the position of an object sometime in the future, you multiply its speed by the time that's elapsed, and you add that to the current position. It turns out, so I heard some mumbling about integration. It turns out that is the way that game engines integrate. Right? No one actually sits down and figures out an integral, right? So you don't have to worry about trying to do that. The more complicated problems are what happens when things collide. And so to actually correctly do that sort of thing, you really do need a second or third course in physics. We'll only talk a little bit about what happens in these cases. But we will talk about how do you detect when things collide. All right, so why do you want physics in a game? And so in many games, it improves the realism of the game. So if you're writing a simulation, so for example, a racing simulation or a flying simulation or a space simulation, you probably want some reasonably close approximation of what's actually happening in the real world. If you are implementing a shooting game or something where things fly in the air, again, you probably want to have some reasonably accurate approximation of how objects behave under gravity. You might want to account for wind, although many games do not. In fact, I'd say most games don't account for wind or air resistance. And similarly, many games involve something that runs around or jumps in the world. You want some crude approximation of the physics that's actually happening there to get a realistic appearance of running, jumping, falling, etc. What do we have here? Okay. And there are some games where the physics is the point of the game. So for example, I've got a few of them here. Polybridge. So, oh, someone actually knows this game. So in Polybridge, the point of the game is to, well, assuming you have, there we go, a network connection. Come on. There we go. Oh, 2080p. Good. Okay, so something's happening, right? So in this game, the point is to build a bridge, right? The bridge, the game has some ability to calculate the physics of an actual bridge, right? And so the point here is that I think typically you're driving or moving something over the bridge. The goal is to build a bridge that actually survives, right? And so in this particular game, the physics is the point of the game, right? There's other games like this or that have where the physics becomes a fundamental part of the game. If you played Portal or Portal 2, there the physics is a part of the game. What else is there? This is Kerbal Space Program. So here the idea is to, you're basically building your own space program. So you're trying to launch stuff into space. So Kerbal Space Program has an approximation, has a reasonably good approximation of orbital mechanics.
We have one simple goal, and that goal is to get to orbit. Let's find out if we do it. So what we have right here is a very small rocket, and some astute observers might say that it's not going to make it to orbit. Well, we're draining fuel pretty quickly here. We're almost at a quarter tank, as you can see in the bottom left-hand corner.
Okay, so basically the idea here is that you're simulating a rocket going up into space. It knows how much fuel it has as you burn fuel. Eventually, I guess in this attempt, they run out of fuel. Rocket doesn't make it into space, right? And so here there's a simulation of the physics that goes on in a rocket. It's a fundamental part of this game. There's a whole bunch of other stuff you can do in Kerbal Space Program as well. Okay, so I guess one of the important things to remember about the current state of computer graphics, which includes video games, is that the actual physics is probably almost never realistic. So physics computations are expensive, especially when you start to deal with things that aren't solid. So anything that is flexible, like cloth or hair, or something similar, water, gas, it becomes extremely difficult and expensive to calculate the physics of those materials. So the goal in at least video games and movies, I suppose, is that you want to have a good enough approximation of the physics that it doesn't break the game immersion, right? And it has to be cheap enough to compute that you can actually compute it on the architectures that you're targeting. Right, so if you're targeting an iPhone, your physics are probably less robust than if you're targeting a high-end PC. Right. So as computing power becomes more and more and more powerful, the physics are becoming more and more and more realistic. But we're still not at the point where you can produce a movie, for example, in real time and have realistic looking and have truly accurate physics. Right. One of your goals here is to avoid the uncanny valley. This, so I guess Nick's example is a little bit out of date here. Sorry. Where'd it go? Here, yes. So regarding the uncanny valley, if you haven't heard this term before, oh, sorry, hang on. If you haven't heard this term before, it refers to the fact that as you make pictures of people become more and more and more realistic, you reach a point where someone looking at the picture starts to feel uncomfortable, right? So the picture looks realistic, but there's something wrong with it. And it turns out we're very sensitive to these things. So The Polar Express was a movie, I forget when it came out, but it's completely animated, completely computer generated. And one of the big criticisms of this movie was that it really was affected badly by the uncanny valley.
All right, ladies and gentlemen. If you please. Shorter in the front, taller in the rear.
So here, oh, drat. How do I pause this thing?
Now, exactly. Columns.
Okay, so if you look at the people in this particular movie, they look pretty good given this is all generated on computer, but they're close enough to looking like real people that they don't look like real people. And so this actually makes a lot of viewers uncomfortable. So a lot of people watching this movie really got turned off by the people in the movie. Let's look closely at the physics that's happening here, right? So...
Of 2, 1, 2.
Excuse me.
So notice the
Question.
coat
What about
belonging
him?
to the conductor and the hair on the girl. Sorry.
No one is required to see
So the coat's not quite moving right. It's moving a little bit, but it doesn't really move the way that fabric actually moves. If you look at the girl's pigtails, they often don't move at all.
Ladies
Right?
and
She just
gentlemen,
turned her head really
you
quick
do
and the
not
pigtails
have to
didn't move at
hold
all.
hands,
Come on.
And
but
so
please
people pick up
remain
on
in
these
your
cues.
columns while
So if you make
we
things
are in transit.
too realistic to the point where people start to notice that, or try to believe that actually what is actually supposed to be what
Look,
they're
you
looking
have
at.
to come with us.
People
She's
become
right.
uncomfortable with the visualization.
Christmas just doesn't
Again, you
work
can see
out
the
for
way
me.
that her pajamas
Never
move.
has.
Not quite right.
But Christmas is such a
Right.
wonderful,
And
beautiful
their hair is
time.
not moving at all.
It's a time for giving and being thankful.
Okay, so commercial physics, so most game engines come with a physics engine built into them. Commercial physics engines, the common ones are Havok and PhysX. So in most of your AAA games anyway, will use one of these two physics engines. And of course, things like Unity have their own physics engine built into them. I don't know if Unity uses one of those two, probably not. And there are, for example, free-to-use physics engines as well. Oh, skip over that. Okay, so what does a physics engine actually do? So basically, physics engines calculate equations of motion, right? And so if you want to move something around in the world, what ends up happening is some kind of crude integration, right? And so I'll show you the mathematics for this shortly. And so in integration, basically what's happening is you're trying to determine the position of an object sometime in the future given its current speed and acceleration, or given its current velocity and acceleration. Another important thing that modern physics engines do is they do this thing called constraint solving. So they work out what happens when one object comes into contact with another object. Right? So for example, if your character is walking up a set of stairs, you don't want the foot to fall below the surface of each step. Right? You want the foot to come in contact with the stair and then go up as they go up the stairs. Right? So you don't want them to float above the stairs. You don't want them to go into the stairs. Right? And then finally, a modern physics engine will do collision detection. Right? So it'll determine what happens when two objects collide with one another. And so most modern, so certainly any real-time game engine, real-time physics engine is only going to work with rigid body physics. Right? And so rigid body physics means that the bodies that the physics engine is computing stuff on, they don't change their shape, right? They're solid. And so this is the most basic and ubiquitously supported. Even the engines that deal with things that flex and move, everything gets broken down to rigid body physics eventually. Right, and so this is all based on Newtonian mechanics, so F equals ma, and the other associated Newton's equations. Right? There are engines that can deal with soft objects, fluids, gases, and things like that. Typically, these don't show up in video games, or if they do, it's a very crude approximation. What's here? MIT, we'll deal with that in a second. Here, for example. Okay, so the movie Brave by Pixar came out quite some time ago now, but it was groundbreaking in the sense that the Merida's hair was very realistic. And so there's an army of PhDs. So all of these people you see in that list there, they all have PhDs. There's an army of PhDs that went into developing the technology that could do nothing but simulate Merida's hair. And so this is a conference paper from SIGGRAPH. It's the largest graphics conference. Basically, in the past, so for every Pixar movie that came out, this was a while ago now. I don't know if it's true today. But basically, the older Pixar movies, every time a Pixar movie came out, one or two or multiple conference papers would show up as well. That describe how they're doing this neato special effect that no one's seen before. And so Merida's hair, this is a pretty famous paper actually, that describes how they went about simulating and rendering her hair. What's here? Okay, we'll get to that in a second. Okay, so what does your physics engine need to keep track of if you want to do rigid body mechanics in a game? And so basically it needs to keep track of the physical properties of all your rigid objects in the game, right? So in Unity actually calls these things rigid bodies, right? And so anything you want your physics engine to work on, you attach a rigid body component to it, and that tells the physics engine, hey, you have to do some computation on this thing. Right? Now here, Dr. Graham is saying it maintains the position, rotation, velocity, acceleration, mass of each object. It actually has to keep track of more than that. And so, back to here. All right, so if you want to keep track of if you want to do reasonably good physics for a rigid body object, you have to keep track of its mass. You need something called its inertia tensor. Anybody heard of the inertia tensor? Yeah, so you normally don't learn about that until second year physics. Right, you have to keep track of its position and its orientation. So that's the direction that it's facing in the world. Right? Position is just in 3D, it'd just be a three-dimensional vector. Right? The orientation is a rotation matrix. You need to keep track of its linear momentum. So that's a quantity that's related to its velocity. And you need to keep track of its angular momentum. That's a quantity that's related to its angular velocity. right? And here's the problem: you don't learn about these things in any detail until second or third year physics, right? You need to keep track of the forces that are acting on the object, right? So here we've got one or more forces F, really, and then you also need to keep track of, if you want to deal with the rotation of the object properly, you need to keep track of the torques that are operating on the object, right? And obviously a lot of this stuff here, it would take several weeks for me to tell you what all of these things actually are, so we're not going to do that. So for our purposes, we're going to ignore the rotational part of the rigid body representation, right? So you don't have to worry about its orientation so much. You don't care about its angular momentum. You don't care about its torque. I have a video about the angular momentum. So I think many of you have probably seen a demonstration like this, but let's just quickly play this video.
When I hold the spinning wheel, nothing crazy happens. But when I flip it, I spin. Flip it back, and I stop. Flip it, I spin. So the question is, why am I spinning?
Okay, so this is an example of conservation of angular momentum. If you want to learn more about angular momentum, you can Google any video about a spinning tire and conservation of angular momentum, and you'll come up with a video that looks something like this, right? So if you want to keep track of if you want to model the rotation of an object in space correctly, you do in fact need to keep track of its angular momentum. We're not going to do that again. Okay, so your game engine is going to, so in Unity, for every rigid body, your physics engine ticks, right? So periodically in time, it updates the physics or the quantities related to the physics of the object. So here in Unity, the physics engine is, it doesn't tick with the frame rate, it ticks with some other fixed update rate. Right, and so Dr. Graham is saying this ticks every 20 milliseconds. Typically, you can't do it for every frame because, again, the physics calculations are relatively expensive to do, which means you can't do them all for every frame. So you do them periodically instead. Okay, basic mechanics as applied to game physics. So to even do a crude approximation of the physics of the game, you need to know a little bit about Newton's laws of motion. Right? And so Newton's got 3 laws of motion, right? Law number 1, direction and velocity of a moving object remains constant unless a force is applied to the object. Right? Number 2, applying a force to an object accelerates the object in the direction of the force. And number 3, for every action there is an equal and opposite reaction. So we'll look at each one of the laws. Right, so the first law is the direction and velocity of a moving object remains constant unless a force is applied to the object. Right, so this is related to this concept of inertia, which is the tendency of a body at rest to remain at rest, or for a body that's moving in a straight line to continue moving in a straight line, right, unless you act on it by an outside force. Right. Okay, so what are forces? Right, and so forces are things like friction and gravity are examples of forces, right? So in this picture here, the basketball player is shooting a ball, right? And so as they shoot the ball, they apply a force to the ball, which launches the ball through the air. As the ball travels through the air, the resistance of the air itself acts on the ball, right? Similarly, gravity is another force. It acts on the ball, right? So gravity is trying to pull the ball down. The air is opposing the motion of the ball in the opposite direction that it's moving in. So this ball is moving in this direction. The air is pushing on the ball in the opposite direction. Right? For the curling example, the curler is going to push on the stone, right? That causes the stone to accelerate in the direction that the curler is pushing it in. Right? As it slides across the surface of the ice is opposing the motion of the stone. Right? So it's slowing the stone down. Using the broom, the curlers can change the surface of the ice. Right? And so to a first approximation, brushing the ice causes the ice to melt. That causes a thin layer of water to appear between the stone and the ice, which reduces the amount of friction felt by the stone. In fact, no one actually knows what's really going on. And somewhat surprisingly, there's a bunch of research related to what exactly is happening in curling. And so a few years ago, does anybody here curl? Some of you curl. Okay, so there was a pretty large debate several years ago about these new brooms that showed up. And so these new brooms showed up, and it turns out that the curlers could use the brooms, and they would have unprecedented control over the path and speed of a stone. And so the brooms eventually got banned, but no one actually knew what was going on. Eventually, some people figured out part of what's happening. And it turns out that the brooms don't just cause the ice to melt, but they actually put grooves into the ice, which now has another effect on the path of the stone. Right? You can imagine trying to simulate this in a video game, right? Are you really going to simulate putting grooves in the ice? Probably not, right? So again, calculating the real physics of things is actually quite difficult to do. Okay, so the basic idea is that if you know the forces that are acting on an object, you can calculate something about the object. Right? So in other words, you can calculate something about its future speed and acceleration. Right? If no forces are acting on an object, right, then whatever the object just keeps on moving in whatever direction it's moving in. So, Newton's second law. Applying a force to an object accelerates the object in the direction of the force. Right? Similarly, acceleration is proportional to the object's mass. This is just if you've seen F equals ma. F equals ma is the mathematical interpretation of Newton's second law. Right? So if you have an object that has if you have an object of mass m, and you apply a force to the object, right, that is proportional to the mass times the acceleration. That. Right? Okay, and finally, Newton's third law: for every force acting on an object, there is an equal and opposite reaction force in which the reaction is collinear to the acting force. Right? So all this means is that in this example here, if you start to, if these two balls collide with one another in midair, right, they both bounce backwards. Right? So when another example is if you push on something, that thing pushes back on you with an equal and opposite force. Right? So I'm standing on the ground. Right? The Earth is pulling me down via the force of gravity. Right? I'm also pushing on the surface of the Earth with the force acting in the opposite direction. Newton's third law. This is yes. So this is sort of Newton's third law. Oh wait, where's the full video go? I have the full video somewhere. Do I still have it? Oh, where's that video? This is actually more conservation of momentum than it is the third law. Okay, so you've got two people. They've both got this one, there's one squishy ball, right? And they're going to run into each other. So these two people look like they have roughly the same mass, but one is moving and the other is not. So let's see what happens. There we go, right? And so what's happening here, it's all conservation of linear momentum in this case, more or less. Right? So the person that's moving has some mass and some velocity. Right? When they run into the ball, that momentum is transferred into the person with the ball. And so in many of these cases, the person holding the ball bounces backwards, but if there's a large difference between the mass and velocity of the two moving people, one of the two individuals gets affected more than the other. So in these examples where there's a usually small woman running into a much larger man, the woman always gets the worst of the effect in this case. So this one I think is particularly bad. Yes. All right. That's fine. Okay. So we need a little bit of math to talk about how you're actually going to implement these in a game engine. Okay, so we need to start out with position, right? So position is just the location of an object somewhere in the world, right? In 2D, it's represented with a two-dimensional vector, right? X and Y coordinate. In 3D, it's X, Y, and Z, right? A three-dimensional vector. So Dr. Graham is writing these vectors in bold. So anywhere you see a bold symbol, that indicates it's a vector quantity, right? So anything not in bold is a scalar quantity, right? So the x-coordinate and the y-coordinate are both scalar quantities. Unfortunately, he's using the angled brackets to be consistent with the reference that he's using over here. I dislike the angled bracket notation strongly, but anyway, we'll go with what we have here, right? So anything inside angled brackets indicates the components of a vector. Now, you also need to know a little bit about the derivative of a quantity. So the velocity is just the time derivative of position, right? So in other words, it's the rate of change of position. So the velocity v, which we're writing as p dot, is just the derivative of p as a function of time. So that means it's dx dt and dy dt, right? You're going to differentiate. So if you know the position of an object as a function, right? Conceptually, if you differentiate the function, you get its velocity, right? Now, in a game, you don't actually know the function that describes, you probably don't know the function that describes the position of an object. Fair enough, right? But you do know its velocity, right? You know its position, you know its position, right? Okay, so if you know, right, so given that the velocity is just the time derivative of position, right, then if you differentiate the derivative, you get back the position, right? So the indefinite integral of your velocity function with respect to time, right, gives you back position. It turns out that, turns out that we need some way to calculate this thing here. Right? Similarly, your acceleration is just your rate of change of velocity. Right? So the second derivative, so the derivative of, come back. So the derivative of your velocity with respect to time, right? So dp dot dt is just your acceleration, right? And so that's also the second derivative of your position as a function of time. So dx dt squared, dy dt squared, or I guess d2x dt squared, d2y dt squared, right? Fortunately for us, you often ignore the acceleration, but we'll see that in just a second. Okay, so we're going to come back to, We're going to come back to this thing in just a second. Okay, so we've already talked about these when we talked about motion earlier in the course, but let's go over them again. If you've got a vector A, we can calculate the length of the vector A, right? It's just the square root of the sum of the squares of the components, right? The same is true in 3D, right? If you have a three-dimensional vector, its magnitude is just x squared plus y squared plus z squared, take the square root. So for example, the magnitude of the vector 3 minus 2 is just 3 squared plus minus 2 squared, take the square root, right? And that's roughly 3.6. Okay, normalized vectors are very useful in computer graphics applications. So if you're given a vector A, the normalized or unit vector pointing in the same direction of A, well, it points in the same direction of A, but its magnitude is 1. Right? And so you can easily calculate the normalized or unit vector corresponding to A, right? You just take A, right? And you find the vector that points in the same direction that has unit length, right? So if you take A, you just divide by its magnitude, and that yields the unit vector pointing in the same direction as A, right? And again, we saw this earlier in the course as well. I think he has a little exercise here coming up. And so if A is the vector 3 minus 2, right, and you want the unit vector corresponding to A, right, you just compute the magnitude of 3 minus 2, 3.6, right? Divide each of your components by 3.6, and there's your unit vector, right? So if you have a velocity, Remember, we can decompose velocity into speed plus direction, right? The speed is just the magnitude of your velocity vector, so it's the magnitude of p dot, right? The direction is just the unit vector in the direction p dot, right? And so I think he's got a little, yeah. You can easily calculate this, right? So, come back. Sorry. Okay, so to solve this problem, the speed is just the magnitude of 4,3, right, which is 5, right? 16 plus 9, take the square root, so it's 5. So your speed is 5. Your direction is 4 over 5 and 3 over 5, right? Okay, the dot product. We also talked about this earlier in the course. And so the dot product, the geometric interpretation of the dot product. So if you take the dot product of A hat and B, right, there's a bunch of ways that you can interpret what the dot product is, right? So Dr. Graham is saying that the geometric interpretation here is the distance in the direction of A hat traveled by following B. So in other words, if you walk along B, and as you're walking along B, you shoot a perpendicular line out towards A, right? When you get to the end of A, you end up getting the dot product. So in other words, there, right? So when you compute, if you take the perpendicular line that hits the end of the vector A, your dot product is the length that you've traveled along B, right? The same is true if you travel along A, right? So if you're traveling along A and you take the dot product with B, right, so you shoot the perpendicular line out to B, this would be the dot product here of, yeah, that's the same thing, right? Okay, so how do you calculate the dot product? So if you have vectors A and B and you know their component form, right, the dot product is you just multiply the x components and their y components together and you add the two values together. So computing the dot product is mathematically straightforward. Right. So again, another little exercise. You've got two vectors here. Compute and graph A hat dot B. So the graphing part, I'm not sure what he means, but that is A here is, you can imagine, is almost the vector 5, 5, right? So it's going to point out 45 degrees. B is sort of that vector there, right? 8 units this way, 3 units this way. Sorry. Right, 3 units that way. So that's basically the dot product here, right? It's going to look the same when you actually draw out 5, 5 and 8, 3, right? What is its magnitude? Well, it's just 5 times 8 and 5 plus 3, so 40, so, sorry. 5 times 8 is 40, plus 5 times 3 is 55, right? So the magnitude of the dot product is 55. The interesting case is this one here, right? If you have two vectors and their dot product is 0, what does that mean? It means they're perpendicular to one another, right? So if you use the geometric interpretation, come back. So if you use the geometric interpretation, right, where that distance there is equal to the dot product, right? For that distance to be 0, what does it mean? Either A has magnitude 0 or B has magnitude 0, right? Or A is perpendicular to B, right? So if A is perpendicular to B, right, then when you draw the perpendicular line connecting B and A, right, the distance you get is 0. Right? And so if the dot product is 0, you know your two vectors are perpendicular to one another. Okay, so that fact there also lets you do other things like, so if you look at the sign of the dot product, you can tell if the angle between the vectors is greater than 90 degrees, right? If the sign of the dot product is negative, then you know that there's a greater than 90 degree angle between the two vectors. So you know that one vector is pointing in the direction sort of opposite to the other vector. Right. Okay, the integration part. So imagine you know your velocity of an object as a function of time. So this isn't velocity, this is actually speed. So this is a little misleading. So this is the one-dimensional case. So you have something moving in a straight line, right? And you know how fast it's moving along that straight line as a function of time, right? So we know that the speed is just the derivative of its position with respect to time, right? And so if you integrate that function, so if I integrate this function here from t1 to t2, right? So if I compute the area under the graph, right, that tells me how far we've moved, right? So what is P2, right? P2 is equal to, so you integrate your velocity with respect to time, right? This is at time t1, that's at time come back. Time t1, time t2, right? So integrate velocity with respect to time, compute the definite integral over the interval t1, t2, right? Add back in the original position, and that gives you your position at time t2. Right? Okay, so there's a bunch of problems with this when it comes to using this in the real world, right? Number one, you need to know the velocity function, right? Typically in the real world, you don't know the function. You don't know the mathematical form of the function, right? You might be able to measure it, right? In a game, you're setting it, so you know what the velocity is at each, you know what the speed is at each point in time, right? Okay, so you almost never evaluate this integral mathematically, right? So instead, what you do is you evaluate it and computationally, right? So to do this integration, right, you can approximate what's happening here, right? So to do the integration, what you can do is, okay, so you can, to integrate this thing here, right, you can imagine filling in a bunch of rectangles, right, and then summing the areas of the rectangles. Right? So how do we calculate each rectangle? So we're going to, at this time right here, right, we're going to take our speed, so p dot, right, and the width of this interval is delta t, so that's how much time has elapsed, right? So the area of that rectangle, oops, is just delta t times the velocity at that point right there. So that gives us our first rectangle. What about our second rectangle? So I'm going to take our velocity right there, right, multiply it by some delta t, and that gives me the area of the next rectangle. Right? Then at the next time point, right, I'm going to take our current velocity, right, multiply it by our interval length, and that gives us our next rectangle. Right? You can see here we've got too much area. Right? We're overestimating the integral in this case. Right? And so on and so on and so on and so forth. So when your speed is slowing down, right, you're overestimating the velocity each time over the range of delta t. Right? And so this overestimates the area under the integral if you're slowing down. If you're accelerating, it underestimates the area under the integral. Right? So that's called the explicit Euler equation here. Right? So to calculate the position at the next time step, take your current position and your current speed. Right? Take the speed, multiply it by the interval over which you're moving, right? And that gives you an estimate of your new position. Okay, you can also do the following. So to calculate your position at the next time interval, right, take your current position, right, and your velocity at the next time interval. So in this case here, the first rectangle is not going to change. So what you're going to do here, if this is p of t, so this is our current time interval, right? I'd like to know what is my position in the future. So I'm going to integrate this area, the area under the function here. To do that, I'm going to look at the velocity or the speed at the next time point, which is going to be over here. Right? I'm going to multiply that by delta t. In this case, I'm going to get the similar rectangle. Right? For the next time step, so if I'm here, right? So at this time point here, to calculate the integral, I'm going to look at the velocity at the next time point. So I'm going to use this point here, multiply it by delta t, right? And I'm going to use the rectangle there. So it's going to underestimate the area now. Right? So in this, if you're using implicit Euler, you underestimate the integral as you slow down. You overestimate it as you speed up. Right? And so these are two simple ways of calculating position given time. Calculating your position given you know the velocity of your object. Right? And so this is the formula that we used earlier in the course. So when you are moving along in a straight line, right, with some given velocity over some time period t, right, you just take your speed, your velocity, multiply it by t, add it to your current position. Okay, so to show you what's going on here, this is an example of what's happening. So what's happening here is that you're simply, go on. Yeah. All you're doing here is basically calculating an integral, right? You're calculating the integral by approximating the area under this function using a bunch of rectangles. So if you, to calculate any simple integral, you can play the exact same trick, right? If you know the current position and the current velocity or current speed, right, you can use those two pieces of information and guess at your position in the future. Your guess is probably wrong, right? Or it's probably inaccurate a little bit, right? And so here's an example of a pendulum. So this is a simple pendulum that you might have encountered in high school physics, right? And so in high school physics, you're given an approximation of how the pendulum actually moves, right? If you actually work out the equations of motion for a real pendulum, it turns out you can't actually analytically integrate the formulas to give you a nice looking formula that predicts the position of the pendulum at some point in time. So what do you do? Well, you can pull out Euler's method and try to use Euler's method to calculate the position of the pendulum at each time in time. So this is what happens if you use the explicit Euler technique to do this. The equations look a little bit different, but it's all the same idea, right? So this is a pendulum, right? There's no forces acting on it except for gravity, so the pendulum should never spin all the way around, right? Unfortunately, in this case, it does. Right? So remember, there's nothing acting on the pendulum except gravity, so this should never happen. Right? But if you integrate the pendulum equations using an explicit Euler formulation, what ends up happening is it ends up spinning all the way around. And then this gets faster and faster and faster and faster. Right? What's actually going on? So remember, as it slows down, right, it overestimates the velocity. Right? And so as the pendulum is going back up towards the top of its swing, right, we're overestimating how fast it moves, which causes it eventually to go past the top, and it goes around and around and around. Okay, so you can improve the accuracy of this by shrinking your time step. Right? So if I make these rectangles smaller, you can actually get this integral to become better and better and better. Right? If you make the interval infinitesimally small, that's the definition of integration. Right? But obviously, as you make the time step smaller and smaller and smaller, you have to do more and more and more work. So that doesn't really help us in real-time situations. Right? Okay, so that's going to be our formula for integrating position, or integrating velocity to get position. Right? We're just going to use the current position, the current velocity, multiply it by the time step, and that gives us our new position. Right? That delta t comes from your physics engine, right? So if it's called every 20 milliseconds, then your delta t is 20 milliseconds. Okay, so in many games, the speed is for the objects that are moving in many games, this isn't so true. This isn't that true now, but not so long ago it probably was, right? The speed of objects was basically constant, right? Or at least limited to a few values, right? So I guess in the original Call of Duty, you only had 4 speeds, right? You either stopped, in which case your speed is 0, you're crawling, you're walking, or you're sprinting. So there's only a small number of speeds. They're all constant, right? If your speed is constant, then the integration is exact, right? Your velocity times delta t gives you the exact integral. So you get the correct result in this case. Right? The problem is when your speed is not constant, right? So if something's falling, it's falling under the force of gravity, right? Which means its speed is not constant. It changes over time, right? And now you have to do something. Now you have to do an actual integration of some kind, right? So in games where the physics becomes important, right? So in particular racing games, so if you're simulating a car or simulating a plane, in this case, this is San Andreas, so you're driving around on a bicycle of some kind. Your speed of the object is not constant, right? Now you have a problem of you don't know what your velocity is, right? So you don't know your velocity is because it's constantly changing. And so what happens if you don't know its velocity? Well, now you need its acceleration. Sorry, what time do we have here? Oh, we should stop here. So I guess we'll pick up the lecture from this slide on Thursday.